Did you get the PDF copy of the book online? Anyone downloaded? Anyone?
No, sir.
Why? It's been around 1 week. Download the book. Okay, it is available online, and you start reading. It will become easier with time. Okay. The book is essential. Okay, without book, you will not get the concept clearly. Okay, so my suggestion is to go and download the book. Okay, and you start reading from now. And since you don't have the lab, but if during some time in between this semester, I can give some demo about the VLSI, different VLSI tools that can be used for designing circuits and chips. Okay, that would be just for illustration purpose. That will not be an essential thing. Okay, but I will try to do that at least, so that it will at least keep you motivated. That okay, these are the things, these are the tools that are actually used for VLSI designing. Okay, sometime later. So yesterday we had seen about different layers of abstraction and information that each of these layers give. Then we saw the simplified design flow. What are the main steps that we follow during the design of VLSI chip or VLSI circuit? Then what is Y chart and what are the different three domains? What are the different three domains? Uh, and how are they interrelated? Uh, we had seen this Y chart also yesterday. Okay, then the design hierarchy also. The concept is divide and conquer. Uh, the thing is that to divide a big complex design into smaller parts and even some more smaller parts, unless the parts becomes easier to manage, easier to design, and then we combine those parts properly to get the final structure ultimately. Okay, so this was the concept. So we had seen some examples also in this. This is a geometrical also seen, and this is the actual layout that is done, that you will obtain at the last phase of VLSI design. Okay, flow. And this is the actual this is containing the structure for actual transistors. Okay, and all the interconnections, those things. So let's continue with this. There are some principles called as structure design principles that are very important according to VLSI design methodology. Okay, and hierarchy is obviously one concept that can be used uh, for breaking down a complex system into a smaller ones and then designing the things. It involves divide and conquer approach, and makes the design it makes the designing of complex systems easier. Okay, apart from this we have three more concepts which are very much important from VLSI design flow point of view. The first one is about regularity. It's called as regularity principle in VLSI. Okay, so it says that the hierarchical decomposition of a large system should result in not only simple but also similar blocks as much as possible. Okay. If we are decomposing a bigger system into a into smaller systems, okay, then we try to decompose in such a way that we get smaller blocks. Okay, fine. We will get smaller blocks, but the emphasis should be on such that we also get similar blocks. Okay, because once we design with the similar blocks, then it becomes easier to replicate and connect them. Okay, so like you know that we can design any circuit, any logical equation with the help of just NAND gates or NOR gates. Okay, suppose the design consists of only NAND gates. Okay, so in that thing, in that circuit, only NAND gates are required. Okay, you will need to design one NAND gate and just use the replication of that gate to construct the whole circuit. Okay, just an example. Okay, but we should do it as much as possible, although it is not achievable all the time, but we should try to achieve it as much as possible. Okay, and regularity usually reduces the number of difficult modules that need to be designed and verified at all levels of abstraction. Okay, it can exist at all levels of abstraction. Okay, for example, at the transistor level, that is at the bottom level. Okay, at the device level, uniformly sized transistors simplify the design, and at the logic level, identical gate structures can be used. Okay, so we can use we 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 should focus on using uniformly sized transistors at the device level, circuit level, and at the logic level we should have a concentration on using identical gate structures. Okay, so the funda is to use simpler and similar blocks. Okay, whenever we are decomposing a large system into a smaller ones. Okay, for example, look at this example. So this figure shows a design of 2:1 mugs. This one. So this is a 2:1 multiplexer. Okay, so multiplexer is a device is a circuit which passes only one of the signal from the many available input signals to the output, and which signal will be passed is decided by a control signal or select signal. Okay, this definition, you are aware of this. Now this simple 2:1 block can be designed with the help of and or an inverter gates. Okay, but here this design shows that this 2:1 multiplexer is being designed with the help of this is inverter block, and these are tri-state buffers. Okay, why is noise coming? Someone. Okay. Okay, chalo. So although we can use different types of gate, we can use AND gate, OR gate, NOT gate to design our 2:1 multiplexer. That's fine, but here it has used how many types of gates? This circuit has used only two types of gates. Okay, one is inverter and the other one is uh, the tri-state buffer. Okay, we can also do this design by using AND or an invert. So that will involve how many types of gates? Three types of gates. Okay, but by using this concept regularity, which says that okay, we should try to focus using similar gates. Okay, So here, this tri-state buffer, this tri-state buffer are same. Okay, inverter and inverter are same. So it uses less number of gates which are similar. Okay, which are also similar as compared to a simple design which will use AND gate, OR gate, and inverter. Okay, so the figure shows regular circuit level designs of 2:1 multiplexer and a D type, this one, the D type edge trigger flip flop. Okay, note that both of these circuits were designed by using inverters and tri-state buffers only. So this example also shows the similar thing. Okay, that this circuit, which is a D flip flop, Okay, you are aware of what is a flip flop. A flip flop is a circuit that will store some amount of information. Okay, a flip flop stores one bit of information. So it's a D flip flop which is being designed by using again the same blocks that was used here in multiplexer. Okay, look at here. This is inverter. This is inverter. This is tri-state buffer. This is tri-state buffer. Buffer. Inverter. Tri-state buffer. So the whole design can be uh, designed, constructed with the help of just two types of gates. Okay, one is inverter, and the second one is uh, tri-state buffer. Okay, but you had seen earlier the circuit of a D flip flop, and it could have been designed with the help of AND gates, NOT gates. Okay, also with the help of OR gates or NOR gates. Okay, so I mean to say that for the same design, different types of circuits can exist. Okay, but out of those different choices, which choice is better? We go for that circuit which uses similar number of uh, gates as much as possible. That is what this concept of regularity says. Okay, so regularity usually reduces the number of different modules that need to be designed and verified at all levels of abstraction. Okay, so when we use similar kind of blocks, so it also simplifies the whole process as a whole at all levels of designing process. Okay, then the next concept is about uh, making the things making the design go parallel. Okay, this is called as modularity principle. So it says that the various functional blocks which make up the larger system must have well-defined functions and interfaces. So if in a large system, we know that it will always happen. Okay, a large system will consist of several small blocks. Okay, so all of these small blocks, which is actually making up the large system or the large chip. Okay, all of these small blocks should have well defined functions and interfaces. Okay, as much as possible, as much as possible. Okay, so modularity allows that each block or module can be designed relatively independently from each other. So with the help of this property, if all of these smaller blocks are having their well-defined functions and interfaces, so it means that these blocks can be designed independently. So this is, let's say this is module 1, module 2, module 3. Now the designing of these three modules can be done in parallel to each other. One team, Mahesh, I think your video is on. Is he driving? Hmm? Mahesh. Okay. So the designing of module 1, 2, and 3 can be done by different teams at the same time. Okay, that will help in saving the design time as a whole, and they can be put on the chip after designing. Okay, so it helps in saving the whole overall design time, which takes in designing the whole chip. Okay, so all of these blocks can be combined with ease at the end of design process to form the large system, right? So what happens is that this enables the parallelization of the design process. If the things uh, get start to be designed in a parallel process manner, that helps us to save the precious time which is there involved in the designing of these chips. Okay, so this one, and the last one is called as locality. So locality, as the word uh, indicates, that it has something to do with the local. Okay, locality means the things which are present nearby. Okay, or the circuits or the blocks which are present nearby to a particular circuit, the neighborhood, and also within the sub blocks. So it deals with the internal, it tells about the internal details, that internal details remain at the local level. Okay, the concept of locality also ensures that connections are mostly between neighboring modules, that the interconnections, we know that those modules should be interconnected with other modules. Okay, without interconnecting we cannot achieve any functionality. Okay, so all those smaller sub modules, they must be interconnected to the other modules. The effort is to have the connections that are mostly between neighboring modules. Okay, and why is this so? So that we can avoid the long distance connections as much as possible. Okay, so the thing is to avoid long distance wiring connections between different submodules. And why is it so? Because even those very long distance connections inside the chip, they also introduce delay, which is significant in the operation of chip. Okay, their delay is now with the most advanced technology, as the technology is moving from 50 nanometer to 7 nanometer. Okay, the technology node is moving. So with the new technology, new latest technology, the delay of the device and the delay of those interconnections are coming out to be comparable. Okay, so the device also introduces some error, delay, and at the same time the connecting paths or the connecting wires are also introducing errors, delays in the operation. Okay, so we should avoid long distance connections within the chip in order to make the chip a bit faster. Okay, and this is extremely important for avoiding long interconnect delays. Okay, as the technology is going down and down, I mean to say that as the device sizes are becoming smaller and smaller, okay, within range of few nanometers, okay, it becomes very very important, extremely important, to avoid these long distance interconnections. Okay, this is one of the most important thing that is to be taken care in the present day chip designing process. Okay, so what happens, although it is not possible always, but what can we do is we can at least, uh, with those operations which are time critical in nature, the time critical operations can be performed locally without the need to access distant modules or signals. Okay, and if necessary, the replication of some logic may solve this problem in large system architectures. So these are some advanced topics where you will get to know that okay, to get some work done, what are the different strategies. Sometimes we introduce some extra hardware within the chip, or sometimes some logic is replicated, okay, to solve a particular problem in a large system architecture. Okay, so these are the things, important concepts: locality, modularity, and uh, regularity. Okay, these are some important concepts from design point of view. Okay, and they have their impact on the design process, on the uh, performance of the chip. Okay, now the next topic is to study about different VLSI design styles. Okay, so till now we had seen something about VLSI design flow. Okay, that gave us introduction about what are the important steps. Okay, what are the different levels of abstraction, and what kind of information we get at each of those levels of abstraction. Okay, now there are different VLSI design styles, okay, which are actually used for designing the chips. Okay, a chip or a particular circuit can be designed by using different design styles. Okay, so there are different types of methodologies. For example, full custom, semi-custom, then programmable. In semi-custom, we have standard cells based. Then we have mask gate array based method. Then we have FPGA on one hand. We have CPLD. Then we have PLD. All of these are having different kinds of design flow. Okay, all of these are different kinds of design styles, and you'll find that some of these design styles are giving us results faster as compared to other ones, but at what cost? Okay, some are fast in nature. Okay, some are cheap in nature, but there is some loss. Okay, there is some disadvantage. For example, you'll find that full custom, okay, where all the things are made from scratch, it will give you the fastest chip possible among all these VLSI design styles. But at the same time, it will also consume a lot of time. It will consume the longest time among all these VLSI design styles. It will consume a lot of money also. It costs a lot to use this full custom designs. Okay, for designing a chip. So what is the use? For example, there are certain uses. All of these design styles have got their particular use. Subra sir, he sits there. Huh? Huh? That room. Look in that room. Look into. Okay. So, for example, the microprocessors chip, which are to be manufactured or fabricated in millions of numbers. Okay, so those chips which are to be produced in very large numbers. Okay, those kind of chips can be designed by approaching full custom design style, because there the performance matters. We need to design fast microprocessor chips. Okay, and we need to produce millions of numbers of these microprocessor chips. Okay, so for those kind of applications we can go with full custom, but there are certain applications where we require the chip in a very short span of time. For those things, FPGA is a good alternative. It will give you the design, the whole design tested, verified, and all those simulations within a few days. Okay, so there are these are different kind of design styles, and we will see all of these one by one. Okay. So for example, the first one is full custom design style. So let's start with this. Obviously, this is the oldest and most traditional technique. Okay, and what is important here is that everything is built from scratch, including the library. Okay, ultimately, the circuit will consist of some components. Where are these components coming from? So where are the gates? For example, NAND gates, NOR gates, XOR gates, AOI gates, then multiplexers, flip-flop registers, all this memory. Where are these blocks coming from? Obviously, they should come from some library. So our library is a collection of those components, and from that library, we can pick up the components desired and construct the circuit by connecting them properly. But even library has to be designed in this full custom design style, because everything is built from scratch. So the entire mask design is done anew without use of any library. Even the library has to be constructed. All those smaller components, all those primitives has to be constructed here from scratch, and that is why it takes a long time. It takes a huge amount of time and effort and money to design a particular chip. Okay, so full custom design is a methodology for designing ICs, integrated circuits, by specifying the layout of each individual transistor and the interconnections between them. Okay, however, the development cost of such a design is prohibitively high. So naturally, if we are doing all the things from scratch, if all the things are started from zero level, then it will involve huge amount of time, it will involve huge amount of effort, it will involve huge amount of money, cost also. Oh, okay. So the full custom design potentially maximizes the performance of the chip, but at the same time, what is the result? What is the advantage? The advantage is that we get a chip, we get ICs which are having the maximum performance possible. Okay, so this potentially maximizes the performance of the chip and minimizes its area with the least amount of area that it can occupy, but is extremely labor intensive to implement. But it is extremely labor intensive. It requires a lot of effort from the employees, from the designers, from the engineers, okay, to get the things done. The full custom design is limited to ICs that are to be fabricated in extremely high volumes. So it is not, obviously it is not advisable to adopt full custom design style for those ICs which are to be produced in a few numbers of quantity. Okay, because that will be a total loss. Only those ICs which are to be produced or fabricated in very high numbers or very high volumes, for those where ICs, this full custom design style is adopted. So notably, certain microprocessors and a small number of ASICs are designed with the help of full custom design style. Okay, so ASIC stand for, you can write ASIC stands for application specific integrated circuits. So the ICs which are particularly useful for a specific application. Okay, so there may be a kind of IC which is specifically designed for communication purpose. There may be an IC which is specifically designed for some kind of DSP, digital signal processing applications. implementation and placement of every transistor is done individually by the designer, the design productivity is usually very low. Okay, typically tons, a few tens of transistors per day per designer. So it's a very low productivity process where one designer may produce a few tens of transistors in a single day. Okay, the next design style is called as standard cell based design. Standard cell based design. Okay, so here we do the designing of the chip of the IC of an IC by using some standard cells or some basic building blocks from a library. So here the library is present. You have a library, and that library contains the basic building blocks which are required, which may be used for designing a big circuit. So the library contains all the required components which may be used, which may be required for designing a particular circuit. Okay, so here there is one thing that library is present. So it uses a standard cell library as a basic building blocks of a chip. So whatever library components are present, we have to use those components and construct our circuit. Okay, so there is one advantage that library components are present. So we do not have to give the time and effort and cost to design the library. The library is already available. But what is the negative point, or what is the downside? The downside is that whatever components are present in the library, they may be efficient, they may be more efficient, they may be less efficient. So whatever type of components are present, we have to go with those components also. But anyways, whatever a standard cell library is there that contains sufficiently, or I may say that it will contain all those components in an optimized form. The library is not there. Okay, whatever is available, you have to pick up those components and design your circuit. Okay, so a typical library may contain a few hundred cells, including inverters, NAND gates, NOR gates, complex AOI, that is and or invert, OAI, that is or and invert gates, latches, flip flops, etc. Multiplexers, adders, those things will be there. Okay, and not only just those components, it will also contain some other variations or flavors of a single block. For example, here, look at here, this is inverter, buffer, tri-state buffers. Okay, so inverters, buffers and tri-state buffers are available in the typical standard cell library, and there are many options, there are many flavors of these gates. So there's wide range of power options: 1x, 2x, 4x, 8x, 16, 32, 64x times the minimum sized inverter. So there would be an inverter which is a minimum size inverters, and all of these numbers represent that its capacity, suppose 4x, so it's the capacity of that particular inverter will be 4 times than the minimum sized inverter. No, if it's not sufficient for you, you can go with again a bigger, 32x inverter, which will be uh, 32 times bigger, 32 times more capable as compared to the minimum size inverter. Okay, so there are various flavors, various types of a single, even a single gate present in a typical standard cell library, and this is applicable for all. Okay, you will get different types of different capabilities of NAND and gates with the range from 2 to 8 inputs, 2 input, 3 input, 4, 5, 6, 7, up to 8 inputs, and with high, normal, or low power options. Okay, so there will not be a single NAND gate, but rather there will be a number of NAND gates available in that typical cell library, and each of those NAND gates will be having a certain kind of characteristic. Some may be more powerful, some may be having higher amount of driving capability, okay, than the other one, and these things. So you have a great choice in terms of number of components and the varieties or and the flavors of components that are available in a standard cell library. So you pick up those components accordingly, okay, and then you can design your circuit. So for example, look at this: NOR, XOR, AOI, complex gates, all of these, multiplexers, adder, half adder, latches, flip flops, they are all uh, available in high, normal, and low power flavors. Then IO pads, input output pads are also present, uh, of having various capabilities for driving between 1 to 16 milliamperes and logic levels. Okay, so the thing is that you will get a variety of components in a single standard cell library. You pick up the component which is most suitable for your design and you use in your circuit. This is the ultimate thing, this is the crux of the story. Okay, so cell based design can deliver smaller, faster, and lower power chips than FPGAs, but has high NRE costs to produce the custom mask set. Okay, so since the library is present, okay, so it will take less time than the full custom design, right? Okay, and as compared to FPGA, it will give us faster chips, lower power consuming chips, but it involves high NRA cost. NRAs stands for non-recurring engineering costs. Okay, so the cost that is involved in a certain design process in initially, which is non-recurable, which cannot be recurred, which cannot be recovered. Okay, so there are some cost involved in the initial phase of a project, which has to be, spent. Some amount of money has to be spent initially to set up the whole thing. Okay, to set up the whole system. Okay, those type of costs are called non-recurring engineering costs. Okay, which is essential. Without NRE cost, without NRE you cannot set up the thing, but it adds cost overall, although it is non-recurable, but it adds cost and it makes the cost higher for producing the custom mask set. Okay, again, it is also similarly it is economical for high volumes of production, where high number of large number of ICs are required to be fabricated. So for those cases we can go with standard cell based design. Okay, then look at here. For example, this I have given just for reference. This is uh, can be, you can visualize it as a single cell. Okay, it's a layout It's a layout of a single transistor. The slide is not coming properly here. Okay. Okay, I will go with this. Look at here. This figure is a typical standard cell layout with some of the constraints. Okay. It will be better in slide full screen mode. This is a simple single cell layout. Okay. Now you will not understand completely, but I know that this is the initial phase. But if you pay some attention here, this is the layout. Okay, this is showing us geometrically the actual shape that a transistor will take on the chip. Okay, so this will is the actual structure of MOSFET that will be fabricated on the chip. Okay, so that is why it is called as layout. Okay, now look at here. uh, in MOSFET we know that we should have a drain and a source. Okay, now this is actually uh, this is one NMOS. This area is one NMOS and MOSFET and MOSFET. Okay. This one represents either source or drain, and this one also that represents also either source or drain. Okay. Now this is actually uh, source which is connected to ground. This is ground bus. So this is contact which is between the source and the ground, and this is the drain of the NMOS. Okay, this one is the P MOSFET area. This I am telling because I know about this. Okay, you will also get familiar with this with time. This is the P MOSFET area. Okay, this is the source terminal, and this is the gate. Sorry, drain terminal. Okay, so we have source and drain terminals, and in between we have gate, right? So this is particularly actually an inverter layout. Inverter. This whole is an inverter layout which consists of one NMOS, one PMOS. Okay. Now this PMOS source, this is PMOS drain. Where is the gate? The gate is in between drain and source. So this black colored hash line, this is actually the gate, and this gate of PMOS is connected to the gate of NMOS. Okay, so it means that we are providing same input to the gate of NMOS and PMOS, right? This is visible here, and here we provide the input A like this. Okay, so and this is the ground area. We should also provide some sort of power. Okay, and this is the power rail called as VDD. So okay, now these are the main components in this inverter layout. In this inverter layout, right? Now, so the height of this cell, the height of this inverter will be given by the addition of all these smaller components. So this is the height of VDD power rail or VDD bus width. Okay, this is the P transistor width. Since this is PMOS, so the width of this PMOS is from here to here, and in between this PMOS and this power we have some spacing, metal to metal spacing. Okay, similarly for N MOSFET we have N MOSFET transistor width and the ground rail width or the ground bus width, and the metal spacing between NMOS transistor and the ground. Okay, and the spacing between this one and this one. Okay, so this is N2P diffusion spacing, the spacing between P MOSFET and the spacing with N MOSFET. So when we add all of these parameters, we get the complete height of this particular inverter cell. Okay, so uh, this I have inserted here just for illustrating purpose, although the main topic is still standard cell based design. And I just wanted to show that, for example, an inverter. The inverter is a gate which will be present in the standard cell library. And how does an inverter look like actually? How the layout of the inverter looks like? It looks like this. Okay. Now here, uh, this is a simplified floor plan for standard cell based design. So what do we have here? Uh, these are the standard. These are the rows. Okay, where the standard cells would be taken from the library and placed. So you will place the components here in these rows. Okay, and these spaces between these rows are available for routing, known as routing channel. The space would be used for the wire connections between different standard cells. Okay, so that is why they are known as routing channel here. Okay, and then there are different squares present around the periphery of the chip, which are known as pin positions. So they will locate the pin input and output pins, IO pins, which will be there on in this chip. Okay, so inside the IO frame, which is reserved for IO cells, the chip area contains rows or columns of standard cells, and between cell rows are channels for dedicated inter-cell routing. Right. So first we place, but there is a challenge here that after chip logic design is done using standard cells from the library, the most challenging task is to place the individual cells into rows and interconnect them in a way that meets stringent design goals in circuit speed, chip area, and power consumption. We have to pick up the components from the library, that is fine, but we have to arrange them in the most systematic manner, in the most efficient manner, so that it consumes the least amount of area and it meets the specifications given by the client for that particular design. Okay, so it is not just a child play to pick up and place it anywhere. No, there are certain targets, there are certain specifications which are needed to be met. Okay, so in many VLSI chips such as microprocessors and digital signal processing, that is DSP chips, standard cells based designs is used for complex control logic modules. So this methodology is used for designing microprocessors and DSP chips. Okay. Okay, so I will take this slide. Uh, this shows a corner of gate array chip which contains bonding pads on its So this is the mask layout of a standard cell based chip with a single block of cells and three memory banks. This is the mask layout. Now look at here. This is the mask layout which will be used for fabricating the actual chip. Okay. So how does it look like? Look, there are three big black regions here. One, two, three. Okay. These are memory blocks. Three memory banks. So these are three memory banks. And with a single block of cell. Okay. And this whole area is a single block of cell. Right. And around this you will find the IO input output pads, IO pads. So these all blocks on the periphery are IO pads, okay, which will be used for connecting the input and output pins coming and going through in and out from this chip. Okay, so the diagram is not very good looking, okay, but we should understand. Okay, this region looks similar, and usually in VLSI chips, okay, these are kind of memory, some kind of memory banks, which are actually more dense as compared to the other area. Okay, so memory banks will always be more denser, more black in color, okay, as compared to other regions, because it contains more densely packed number of components. Okay, so this is the mask layout which will be used for fabricating the chip. Okay, okay. So the mask is very important. I have, I'm giving this emphasis on this term mask. Okay, so keep this term in your mind. This will become clear when we go through the fabrication process. Okay, a mask is very important from the fabrication point of view. Whatever we fabricate, whatever chips is being fabricated, okay, that cannot be achieved without the help of a mask. A mask is a thing which actually transfers the images present on them onto the top of the chip. Okay, so this will become more clear with time. Okay. And next is about gate array design. This thing we will see in the next class. So I'm stopping here. Okay, and I will urge you to read about this full custom design style and standard cell based design style, and try to understand that what are the things going on here. And you can also go and read about gate array design and FPGA based design methodology. Okay, but we will see these things in the next class. Okay. uh, no one is asking any doubt, students? If you are having any doubts, any queries, you can ask. Okay. And we are having around 43 students here, although the strength is 52, I think. So I think um some students are um, mm, not here. Okay, so we should have at least 45 plus strength here. Okay, because attendance is important from this exam point of view. You have to maintain 75% attendance for appearing to semester exams, so do not be lazy on that. Okay. Maintain your attendance, because then at the end of the semester it becomes difficult again if you have short attendance. Right? Anyone is having any doubts, anything he or she can ask. And install Canvas. Okay, I will be using Canvas, and I will give you the code for the course with that. you can join the course, and you can give your attendance in the chat box. Just write your roll number and name and for your attendance part. Okay.